So today we're going to talk about modeling rainfall runoff in GoldSim, from a GoldSim perspective, of course, and in particular for incorporating into a water balance model. And it could be a mine site, or it could be a water demand or supply model for a municipality. But the assumption is that it's going to be a fairly big picture type model, not so much detail that we would be doing something like stream routing, for example. We could, and we do have examples for that, but for these types of models, we're talking about usually 1 day time steps, 1 day calculation steps, or 1 month time steps, or maybe even 1 year for that matter. But these are this is the scale that we're talking about, the time scale we're talking about for these kinds of models. Now, it doesn't mean that you could have shorter time steps than that with these models. You can, but the way that I'll be presenting them are applicable to this larger time step model. Okay, so what I wanted to do today was talk first about a simple watershed yield model, and this is something that would be where we'd be using a 1 year or a 1 month time step, and it's really more of an estimate, and it can be used when we're not trying to do things like calculate a peak flow, or we're just looking at long-term forecasting and need approximate values. Then we'll be talking about the Australian water balance model, which is more detailed and simulates more of the physical process of the runoff from rainfall. And following that, we'll talk about a little bit more involved model, the Sacramento runoff model. And that takes into consideration more about the soil and the soil moisture, and runoff and recharge. So these are the three, and obviously it doesn't cover everything when we're talking about runoff, but these are three good examples, and show you how you might be able to incorporate these kinds of things in GoldSim. So that being said, I will go ahead and continue with the simple watershed model. So let's go ahead and start that up. And this one, get GoldSim started here. Okay, so here's a blank GoldSim model. Just checking to see if there are any questions, and there are not. Okay, good. All right. So, and by the way, if you do have questions, I would be very happy to answer either during the presentation or after. Well, I don't remember the name off the top of my head, so I'm just going to go to the library. Oops, not AWBM, simple. And this one is watershed yield. Okay, so this model you can read about in the by double-clicking on this reference hyperlink here, which takes you to an NRCS document. That's the National Resource Conservation Service, I think is what the name is. But that they are the ones that documented this process, and it's really intended for just calculating a basic an estimate of annual yield. And it says that because a lot of times you're looking at how much water might run off in order to be used, for example, for irrigation. But you might also be looking at approximately how much water might be running into their mine site, that kind of thing. But it's for an annual basis. However, it says in the documentation, well, you can use that number to then derive estimates of seasonal or monthly values. And so that's what this model does. It actually gives you the option to do either one. And depending on the options you choose, you will end up with a different type of answer. So this dashboard was built in a way to give you those options. There are these checkboxes at the top, where if you check both of these checkboxes, then you will end up with monthly factors and some uncertainty incorporated into the model. So let's see what happens when you run it. Okay, so running it now, you see here's a plot showing percentiles of probabilities through time of the runoff rates. And so you can see at some points it might peak fairly high. Now, what is the cause of a high peak here and a very low peak in this year? Well, it's random, actually. And I would imagine that if we ran more realizations, we would get a little bit more consistency in what these peaks are going across. In fact, we should probably just play with that just to see. Whoops, I did not mean that. I meant to just hit that. Okay, so let's go ahead and let's multiply our realizations by 10. So now we're running 1,000 realizations, and well, now we see a very unlikely peak here. But anyway, I guess we're not going to get real consistency just because we'd have to run many realizations. These are very rare events that are occurring here based on the uncertainty that we've been applying. Okay, so if you don't want uncertainty in our outputs, then you just uncheck this box, apply uncertainty, and run it, and you'll see that no matter how many times we run this, we will always get exactly the same distribution over time using these factors that are applied. And these factors are being applied to the mean annual runoff of 8 CFS. Okay, so another thing we can do is you can say, I just want an annual value, and then it just calculates one number. You'll see that this is still a percentile chart down here. The reason for that is because the model is running Monte Carlo and multiple realizations. So if we just ran it for one realization instead, then you'll see you get a chart you might be more used to seeing for deterministic runs. Okay, so there are a few different options here that you can plot like this. And a couple of things I just wanted to note is, first of all, about this dashboard. How do I get it so that if you check a box, something appears? Well, if that's new, let me just make a quick note of that. You do that by applying what's called attributes to the dashboard control. So if I go to the properties of this slider, if I go to the properties of it, then you'll see there's another tab up here called attributes, and then you can check a box here that says hide and disable the control if this is met. And this is just a Boolean where you can set it to true if you check a box, and that's what we've done up here. So if you check this box, in other words, if you check this box, then it will appear. If it is not checked, this will be false. So if this is not true, then it will hide, and that's what it does when you uncheck it. So if I preview the dashboard again, then check it or uncheck it, and it disappears. Same with this one. So that's how that's done. Anyway, so this model is pretty basic, and it's using some assumptions about the uncertainty. By the way, the uncertainty was just added. I just added this to the model. It's not in the documentation. So it's really just here to show that, okay, yeah, you can get these repetitive seasonal values, but if you want to look at something outside of that range, then you could apply uncertainty. And it's just assuming that we can use a log normal distribution, and we can just apply with a slider the standard deviation. You can just increase the standard deviation to give you higher peaks, like that, or you can lower the distribution to make it more consistent across the year and also across the realizations. The other thing you can do is you can say, well, I want the changes, the random changes, to be very random. So you can turn down your autocorrelation factor. Autocorrelation is really about how if you pick a high number yesterday, then you're more likely to pick a high number today if you have high autocorrelation. So as this autocorrelation approaches 1, then the previous sampled position from the distribution will be similar to the position you pick on the next time step. So it makes it so you have something that might kind of have some memory in it, which often happens in hydrology. So it might be a good idea to increase the autocorrelation factor, which gives it a look of having more of year-to-year slow transitions over time. So something to think about. Anyway, so this model could be incorporated then into whatever water balance model you might have, simply like I showed you last time, Control C to copy it all, and then paste it into your other model. And your other model, if it is a daily time step model, then what you'll see are constants over the month. And I'm curious just to see, this is always dangerous to do during a presentation, something I haven't tested, which is to change it to 1-day time steps. Let's see what that looks like. Okay, so that is not the best way to see it. Let's see, watershed yield. Oops, that appeared down here. That's weird. Oh, these are annuals. Let's see if I just right click on that. Let's see, what is this? Seasonal yield. Oh, because it's interpolating on the days. Okay, well, I mean, it's pretty good, and you can see it's interpolating pretty well, but not in all the cases. There are these jumps and it's simply because of the change in the number of days in the month. So you could see that, well, this works on a monthly time step. Switching over to a 1-day time step might not be something you want to do with the way the model is right now. I'm sure it would be a very simple change that we can make to the model, but it's not currently set up for daily. It's really set up for monthly and annual. Okay, so with that, let's go to the AWBM model. But before I do it, well, it's probably good that I show you first, and then show you the outcome of what I'm talking about. So the AWBM model, it's been around a long time. I've given a lot of presentations on this model, and the documentation is really good. So you can look at, by clicking on the elements that have these hyperlinks, you can turn on the notes, and you can read more about them. You can also refer to, let's see, documentation right here. So there's lots of chances to read about this model and how it works. A couple of important points that I want to give here are that this model requires, and it says it here in red here. It says it in a couple of other places, but you really need a 1-day time step for this model to work the way that it's currently implemented. If you go with I'm sorry, I shouldn't have said that. If you have a constant time step, that's what we need. We need a constant time step. The assumption is that your steps are always the same, because that's just because of the way that these equations work. And I will show you later another variant of this model that can totally be isolated from any inserted updated events. But currently, the model will work perfectly under a constant 1-day time step. And if you look at this chart, you can see down here at the bottom, the red and the blue. That's because the lines are on top of each other. It's comparing to the output of another tool called the RRL toolkit, which we have links in here to access that if you want to. Have a link up here. It's called the toolkit.net. It's an Australian tool, or developed in Australia, I should say. And we've compared the output. So it works perfectly for this 1-day time step. But often what happens in GoldSim models is you have inserted events that are occurring. And so what I'll do right now is I will simply go to the simulation settings, and I will allow, first of all, I'm going to allow unscheduled events. Okay, this is the default setup for any GoldSim model. Now, if this is not checked, then you don't have to worry about unscheduled events. They're not going to happen. You don't even have to worry about it. That's why it's unchecked currently in this model. But oftentimes in models, you want unscheduled events for whatever reason. And if you do, then obviously you'd want this checked. Okay, so if this is checked, and I'm just going to show, I want some plots to show us the effect of unscheduled updates. So I'm checking both of these boxes. And now I'm going to also insert, well, no, let me not do that. Let me just run the model. Okay, so I'll run the model with it allowing some inserted steps. We also get this message that says, oh, hey, by the way, you have a time step in your model that is not the same as what you're assuming for your calculations, is essentially what this says. So that's good that this error message is here, because we just want to make sure that you're aware of this. If you go ahead and hit ignore future reminders and just continue, then opening up the chart, you'll see we do not have the same answer anymore. Let me zoom into a spot to show you what I mean. So here's a spot right here. This looks really strange, actually. And it's not really that strange. It just looks strange. The blue dashed line should actually not be doing this. What's happening here is, oh gosh, this is the time series. So the time series output, it probably shows constant value over next. It does. Let me see what happens if we just say instantaneous. I think it'll look a little better. Oh, that was why. Because I just wanted the very, yeah, so this ends 1983, and let me see, model ends 1984. Okay, so let me just add one more row to the bottom of this table. Okay. Okay, so this is where we were before. All right. Okay, so I'm gonna zoom in where we have the discrepancy. Okay, so it's pretty much the same, but this point right here is now interpolated on the time series. This point right here, before, when I had the chart before, it was down here, as you might recall, because we had constant value over next assigned to this time series. So the blue line is really just a time series output from that other tool. And it only has values at midnight of each day. So it has a value here, and it has a value here. But this value was inserted by GoldSim. This is a new point, a new time point. At it says at 7:30 p.m. is when it occurred. And so when another time step gets inserted in the model, then GoldSim has to know how to do these. What does it do when it's in between two values of a time series? And that's why you have to specify in a time series element whether it's constant over next or whether it interpolates. And so now that we're interpolating, it's just a linear interpolation between these 2 points, which is fine. So the blue line is fine, but something else is going on here with the GoldSim output, and that is that because we are interpolating and because we have an intermediate step, it means that our surface stores, essentially the functions that AWBM uses are a different value when you're in between time steps instead of when you are at the at the end of the time step. So what happened here is our surface stores probably did not fill up as high, so they do not calculate an outflow that is as high because we've done it twice here instead of just one time. Okay, so really what we want here is to isolate the AWBM model from these inserted steps. It's just not built for steps that are not constant over time. We would have to redesign the model in order to get it to where it can compute the correct answer no matter when the time step is inserted. And that's just not how AWBM works right now. So what that means is we need to either isolate this model from the rest or isolate the rest of the model from this. And it's actually the latter option is what we need to do. So let me show you what I mean. I'm going to split the screen here so that we have GoldSim on this side and then another GoldSim on the other. And let's just say, for example, that in this model on the right, we're building something new. And let's say we have a the main model. This is where everything's going on, our entire model, except for the runoff, rainfall runoff. And you could even lump some other things in there, some climate models. So for example, if you had a precip model, you would also put it over here. Anything that's requiring a constant time step. So any kind of hydrological model, it probably is assuming a constant time step. So you'd put them in here. Okay, so I'm going to call this runoff, we'll say. Wait, that name might already be used. Runoff calcs, we'll say. Okay, I'm going to localize that. And then I'm just coming over here to AWBM, Control A, Control C, and then come over here to runoff and paste that in here. Okay, so AWBM is in here. Then what you would do in order to prevent the runoff calculations from seeing any inserted events is what you would do is you would put you would put the rest of your model here into, if I double click on this, into a container with an internal clock. And what that allows you to do is specify on this tab, internal clock tab, what's the maximum amount of time between time steps. So you say 1, obviously, because it's a 1-day time step. But what this allows is any inserted events will be smaller than that. That's fine, that'll work. So it will allow inserted events to occur in here, but they will not be occurring over here. Okay, so that would prevent your AWBM model from seeing additional unscheduled events, but the problem that we have here is that the AWBM model in this particular implementation is already set up to insert events. It's already going to insert events the way that it's set up right now. And that's why this model is set up when you first open it with its simulation settings. That's why these two boxes are unchecked, because it doesn't matter whatever kind of calculations you have to insert events that you have, it won't allow them. We do need at this time, I need to spend just a few minutes talking about how these inserted events are created in this model. I know that that's not exactly the topic of runoff models, but it's very important because when you're incorporating these kinds of models in GoldSim, you must be aware of inserted events and their impact on these kinds of models. So I'm just going to start a brand new model, and I'm going to create just a little pond model, very simple pond, and it will have units, quantity units of cubic meters and flow units of cubic meters per day, just keeping it very simple. Okay, so that's our pond, and we'll start it out at, let's just say, we'll keep it 0, and then we'll have an upper bound of, let's say, 10 cubic meters. Okay, then we'll give it a duration of 10 days, simulation 1-day time steps, and then we'll go ahead and put in a stochastic to represent the inflow into the pond. And in fact, that's even going too complicated. Let's just put a static. So inflow into the pond, cubic meters per day, and then let's say a number that's not exactly even. Okay, so let's just call it 1.47, let's say, something that's kind of strange. And in fact, let's go 77. Okay, so we have this number, we're adding that amount every day to this pond, and eventually we're going to hit this upper bound. Okay, so let's see what happens when we hit the upper bound. So I'm going to add the inflow here and run the model. You'll see there's a message in the log file. I'll just skip that for now, and then look at the pond volume, and you can see that there's a bend in the line from day 5 to 6. Let's also add the inflow to this, and then let's look at one more thing, that is the outflow from the pond. The outflow is already available on the pool element. So if I go to add a result, I have to just expand the pond element and click on the overflow output. Okay, so with all of those here, we can see what's going on. And I'll go to the table view. So this shows us that the pond is increasing until it hits 8.8, and then it hits the capacity 10 on day 6. We have an inflow of constant 1.8, and then an overflow 1.8 happening here. So this all seems generally fine, but if you were to actually try to reproduce this in Excel, you might not calculate the same thing, and that would occur right here on day 5. The reason is because it's at 8.8. We only need, what do we only need? 1.2 more cubic feet, and it's actually not exactly right. It's a little bit less than 1.2, 1.15, I guess, until I let's see. There we go. Okay, yeah, that's as far as it goes. Okay, so yeah, 1.15. That's how much more we need in order to fill it up to 10. So the question is, why do we not show any overflow on day 5? Why is there 0? Because it would fill up actually before it gets to day 6, and it does, but the chart by default will not show that it actually fills up. So what's happening here is this line is linear, it gets to this bend, and in reality it's going straight, and it would hit right about where I'm pointing. The reason it does not is because we have this model set up to show us values on 1-day time steps only. 1-day time steps, those are the only times it's going to show us results, but things are happening in between. So if I go to the advanced button here, and you see that it is allowing unscheduled events. If I click on this, then I will be able to see exactly what's happening if I have a chart that's already set up, which I forgot to add. So let me just add that real quick. Pond, inflow, and overflow. Okay, and you see here, there are 2 different units. The Y1 has cubic meters, the Y2 has cubic meters per day. Also notice the display column here, it says high res, meaning it's showing high resolution outputs because we have that box checked in the simulation settings. I run the model, and then I see there are no bends, but it's also showing us a value that does not occur at the change of the day at midnight. It's 5.6 hours. Well, no, sorry. It's 0.65 days into day 5, right? I look at the table view, even better, it shows me exactly the time. At 5.65 days, we hit the capacity of 10 and immediately start overflowing. Okay, so this is really important to see this, that your hydrological models are not going to have this built in. They don't have necessarily, they don't have the ability to adjust the way they're built to these changes in time steps. So what that means is either you need to disallow this, you need to stop allowing these inserted events. And if you do that, by the way, GoldSim will calculate the overflows differently. It'll calculate it as an average over the day, which is probably more in line with how you might do something in, say, a spreadsheet or even some of these other hydrologic models. They will assume that everything's a 1-day time step and not ever change it. And so then what you'd be looking at is the setting with this unchecked. So if I uncheck the allowing of unscheduled events, when you look at the chart, you will see something different. You will see that the overflow, there's an intermediate overflow that's less than the 1.77, and that's because we have calculated on day 5 an overflow that was only occurring for part of the day. Therefore, the flow is going to be less. It's an average over the entire day and ends up being 0.6 cubic meters per day just on that day 5. Okay, so in conclusion, what pool elements and reservoir elements do is they insert an unscheduled event whenever one of their bounds is hit. Either of these bounds. If you hit any of these, either of these, GoldSim inserts a time step and it is impacting your entire subsystem that you're modeling. or pretty much your whole model, unless you have other containers in other subsystems, but most likely you don't. And it's going to be causing every update or every expression in your model to update at that unscheduled time. And so with that, just realize that in an AWBM model, for example, it has these pool elements with bounds, and we'll be hitting those bounds every once in a while. In fact, that's the point of it, because AWBM requires that it's taking the overflow from the surface stores. And so, of course, it's calculating overflows. Those overflows are happening, and those are happening at unscheduled events unless you do not allow the unscheduled events to occur here. Okay, so let's now look at the case where you have to have unscheduled events in your model. If you have to have them, if you have to have this checked, then there is another example of GoldSim available. So if you go to our Help Center, then click on Model Library Applications, and then under Hydrology, go there, and you will see there is the write-up, the article for the AWBM model. So we click on that, scroll all the way down, and you'll see there are two versions of the model, and one of them is the submodel option, and the submodel option allows you to run the entire, calculate the runoff hydrograph at time 0. So it takes whatever time series you give it, and immediately it will generate a hydrograph at time 0, and then it runs the model. Then it's totally isolated from any inserted events that you might have. So this is useful, and it could solve your problem if you have to have inserted events. So let me just show you that model. Okay, so that version looks like this, similar at the top level, but down now here, you see there's a submodel, which, by the way, is triggered to run at time 0. So when that runs, then it holds the value or the output in a time series by linking it to the submodel. So that's the nice thing about having a submodel. While it's fairly complicated, I mean, it's a GoldSim model inside of GoldSim, which is pretty complicated, but the nice thing about it is that you can have it do like a preprocessor, calculate before anything else starts in your model, and then have it generate an entire time series output that you can then use in other places, which in this case we are using that to calculate our total runoff through time, so that this could be then connected to any other part of your model. And it is not influenced whatsoever by inserted events that might be occurring during your simulation. And so this would be a good option if you must have this box checked in your advanced time settings, this allow unscheduled events. So with this checked, then we are fine in this model, because we are using the submodel to do it. And not only do you need, in addition to having this runoff calculation going on in here, you could also have your precipitation model, like we talked about earlier, evaporation model, all of your hydrology, in fact, to be done at time 0. The time you would not want this, or in the case that you would not, the case that you might not is if you have feedback from your main model back into the calculation of runoff. That could happen if, for example, you are simulating perhaps development occurring in the watershed that changes, for example, the runoff coefficient and the amount of infiltration or something like that. Then if your model is doing that kind of thing, then you wouldn't be able to do this as a preprocessor. If you have another part of your model that is calculating trend changes in average annual temperature, for example, then you wouldn't set it up this way, but you could also include that temperature model in the submodel too. So actually, that could still work. So really the only time that you wouldn't want to use this is if you have feedback from the model, from your main model to the hydrology. I think that would be the only time that you wouldn't be able to use this option. So So you should, if you get a chance to look over this this article here, I do encourage you to have a look at both of these models, both calculating the same exact thing, but just doing it a little bit differently depending on your needs there. Okay, so the next model I want to show you is the Sacramento model. Oh, but before I go there, I do want to talk about calibration a little bit. That's not the topic today. November, the last lesson in November is going to be on calibration. So we will cover it then. But I do just want to say that the variables that you can use to calibrate this model are, and in fact, let me open up the other one because it's just laid out a little bit better. Okay, so the main variables are KB, which is the recession constant for base flow, and a larger number, and it's between 0 and 1, by the way, between 0 and 1. The closer it gets to 1, then the faster that this will drain. And is that right? Hold on. Let me see that. It's the other way around. I'm sorry. So it would be because it's 1 minus that. So as that value approaches 1, then the outflow becomes slower and slower, and it starts to approach 0, and that would also cause a more a slower response. You could say a slower and more attenuated response from the overflows coming off of the surface stores. Let me just show you a schematic of AWBM. Okay, so with AWBM, what we have is the rainfall that comes down with some potential evapotranspiration intended to remove any of the excess rain that might not be running off and calculated as total runoff. So some of the water is removed, but the rest of the water falls into 3 different buckets of 3 different sizes, and it's just the way that the model's set up. It does say in the documentation you could add more buckets if you wanted to, if you thought you needed them, but 3 seems to work pretty well for a lot of applications. Okay, so these are filling up over time, and eventually they will each start to overflow. One of them, being the smallest one, of course, will overflow much more often than the other 2. But having the combination of these 3 different stores actually makes it a fairly robust setup to mimic what you might see in the real world. And so anyway, these overflows are then just added together and brought to a point right here where we then split the flows again, depending on a constant value that splits it between base flow and surface flow. Surface flow then goes into a tank, same with the base flow, but they both drain at different rates. They do drain as a function of how much water is in the container, but they drain at different rates using the recession constant, which is simply just a constant multiplied by the amount of water in the tank divided by time is really all it is. So you can imagine as the tank gets closer and closer to 0 volume, then the outflow from it is correspondingly low, going closer to 0 as well. So these 2 tanks never hit exactly at 0. They get close to 0, but they never actually hit 0 there. In fact, they will get so close to 0 that essentially it snaps to 0 when it gets small enough, when the number gets small enough. But in theory, it wouldn't. But anyway, so then you pull water out of both those and it's summed, and that's the total. Now, the recession constant is what you can use to control the rate at which it begins to remove water as a function of its amount. Typically, the base flow recession constant will be a lower number. Let's see, is that right? If that's a lower number, then that is a higher number recession. Yeah. Okay. And then the surface runoff coefficient would be a number that gives you a better representation of something that has higher spikes, runs off faster because it's on the surface. And then you have the K values, and then you have the BFI value, which simply splits the the overflow from surface stores to base flow and surface, and then the surface stores themselves, which is an array. So this is a list of surface stores, 3 of them, and it's doing the calculation for all 3 at the same time in this vector reservoir element. And the capacities of each of those 3 surface stores is in here, and it's shown up here in this data element. So this could also be used for calibration. However, it's been found that you can add these values up to just get one number and use that in your optimization as an optimization or calibration factor that then you use to distribute those numbers to these 3 to here. So just imagine just fluctuating the total, and then dividing up the total into these 3 using factors. That could make the calibration a lot easier, which I will be showing you later. But just keep that in mind. If you're in the meantime, if you're going to do any calibration of AWBM, just keep that in mind. That if you want to include the C factor, that you should probably do it as a total in the calibration. Okay, so let's go to the next model, and that is the Sacramento runoff model. Sacramento soil moisture model, sorry. Okay, this model is somewhat similar. It has a dashboard that you can work with if you want, but you don't have to copy this over to your model. It just makes it easy to work with. So when you run this model, then you'll see there's an output here. You can look at the flow components. So it's divided up into surface flows, again, just like AWBM, surface flow, base flow. The sum of the 2 gives you the green line, the total. Let's see, stores. Okay, so this is similar to AWBM where you have the surface stores. In this case, we have 6 stores, and they have different functions. You have upper zone, that's UZ, upper zone. These acronyms might seem strange, but that's what the documentation uses. So you'll see those factors or those acronyms being used throughout the model. But it's upper zone, which corresponds to over here in the inputs, the upper zone. LZ is lower zone. So that's where those are being used. But no flow, no runoff is being generated ever unless these stores are at capacity. So the overflow is when they start to when water flows to the next one down. In the lower zone, you can have the values being drained over time, and that's when the flow is being generated from the lower zones. And let me just see if that's right about the upper zone. Let's see, if I click on the stores plot and then also look at the runoff plot. Here's the runoff plot. Okay, so if we put these on top of each other, then we see for realization 1, we're looking at the red line, surface store. These should correspond with, let's see, that's January. This is not going to tell us actually. So what we'd want to do is we'd want to look at, okay, I should probably describe a couple more things. The entire model is, well, all the calculations are done in a script element. So if you're kind of new to a script element, you just get that by going up here to the functions category and then clicking on script here. And what that allows you to do is a whole series of calculations row by row using just definitions, basic definitions and assignments that can be expressions like this, also if statements can be added, and it's a very structured way to write a script. Actually, it's not just freehand, blank text editor, for example. You add these lines in a controlled way, and that way it's pretty hard to put the wrong syntax in, because even if you add an if statement, let me just show you what it looks like when you add an if statement. It gives you just a dialog here. It generates the if then end if, but then you can put in your expressions. You can even say, oh, I want an else clause. And then when you do that, it will put the else in for you. See, all of this stuff is just added very simply. So it's a pretty nice way to write a script. It's pretty straightforward. But you can see there are a lot of calculations in here. But I have made it possible for you to see all of the outputs as a vector. And you can see up here at the top, we have the starting positions of everything. These are all the different stores that we have, upper zone, lower zone. And if you click on the output port and you expand the main results, you can see that here are the all the individual items. So now when we run the model, we can look specifically at, for example, the upper zone and see what those flows are. So now this is just the upper zone capacity, but it's not the flow coming out of the upper zone. But the flow coming out of the upper zone is what's contributing to the discharge. And the discharge is calculated in here. Discharge, total outflow, there it is. So we could go back and look at how we're calculating the outflow. Here it is, total outflow equals surface plus base plus or minus ET. That's how it's calculated. You can also go into the model verification and see how it compares to other tools. In this case, the model was built based on some code written in R, and that is pretty much what drove all the calculations in GoldSim, is really just copying the R script functions. And you can see that it's got an exact match to the R output, but an approximate match to the RRL toolkit. And I have still not been able to conclude what exactly is causing those minor differences between GoldSim R and the RRL, but you can see that they're pretty close, and actually looks pretty good. But if you want to take on a project and see if you can find out why the RRL toolkit is different, I would very much appreciate knowing what the difference is. But and it could be just my misunderstanding of how the model is set up in the toolkit. But let me just show you the inputs. Here's a screen capture of the inputs I put into the RRL toolkit, which are the same that I have in the model and in the R code that was run. So I still have not gotten to the bottom of that, but I have used it in it for real application and was able to calibrate it to match observed flow values. So it appears to be working pretty well. And if you're looking for something that looks at a little bit more detail than what AWBM uses, then I would recommend this model. Okay, so as far as tying everything together, I did want to talk a little bit about that. So far in these lessons, we've talked about precipitation, temperature, evaporation, and now runoff. All of those things can be applied to this to calculating runoff. So, for example, this model, the Sacramento model, it needs a whole bunch of inputs. But let's just go to the simple the AWBM real quick. Okay, so this model just needs precipitation and potential evapotranspiration. So just imagine if you copy and paste this model, which we've done over here, copy and paste it over here. Imagine that you could also, in addition to what we've put here, we could now put, for example, the WGen model in here that would generate rainfall that we could then replace this time series with. We could then calculate potential evapotranspiration using the models that we talked about last week. Or you could calculate evaporation by putting in a temperature model. Well, actually, WGen generates temperatures. So WGen could drive everything. and you could add the evapotranspiration model that we talked about last week, put that in here, and then have all of that drive your runoff calculations and come up with a whole wide range of possibilities that are all within reason, because those other tools are built on as a function of observed historic records. Okay, so with all of that being done, then that would lead us to next week's topic of calculating water demands. So we would need a lot of the tools that we've talked about already to calculate water demands for your model. So if you have not done so yet, I highly recommend that you go to our webinars page. So that's here on our main GoldSim page, customer care, learning resources, webinars, and then scroll down and make sure you register for next week's lesson, municipal water demand. So that's on October 1st. And then after today, I will put the archive, put the video recording here. So you can look at that later. Anyway, that concludes the presentation today, and I will stick around for a bit to see if you have any questions. Thank you for joining, and hopefully I'll see you next week.